Okay, so I'll start. I'll first introduce myself. My name is Yaron. I'm a CTO and founder of a company called Iguazio. I won't focus too much on what we do. I'll focus on how we do things, which are a bit different in this cloud-native community. We're more of a real-time system, and we had to do a lot of hacking to make sure that we sort of live on one end with the cloud-native architecture. On the other end, we maintain real-time performance, and we have to hack through the different layers of networking, storage, and IPC. Prior to my role in Iguazio, I was a VP data center in a company called Mellanox. Mellanox is one of the leading vendors in the networking space. Many of the cloud service providers, database vendors, storage vendors use Mellanox for networking equipment like NICs and switches. And sort of my role was working with all the open source communities, OpenStack, and cloud vendors and all that. So this is a lot of my background comes from there, and this is you'll see a lot of it comes in the slide. So I won't just reflect on what we're doing in the company, but also some of it around my background with prior architectures. So first, how does our architecture look like? What are we doing? We're building a data platform. I'll spend just a few words on it later, which is an extremely high-performance data platform. This is something that delivers millions of transactions per second, 100 gigs of throughput. And 2-3 years ago, our chief architect, when we started, said, you know what, there's this crazy idea of cloud native. Let's put everything in Docker containers, so now it can be elastic and all those cool ideas. And let's break everything to just small, tiny microservices. Said it's probably too many microservices, a lot of energy in RPC. Said, no, it will be fine. So we really design everything from day one as microservices. So if you look at our architecture, there are things around the platform services, which probably many of you guys have, with using standard tools like Elasticsearch for logs, RethinkDB for sort of our configuration, etcd, RabbitMQ. We use Graphite, but we're going to move to Prometheus later on. Those are sort of the traditional things. Everyone has API servers, which basically serve the traditional configurations. And also, what's more unique about our architecture, we have sort of the high-performance data path, where we have like Nginx that deals with data transactions. We support many traditional data transactions, like we support Kinesis, DynamoDB, many of the traditional Amazon APIs, just much, much faster. And we have the data nodes, which are the things that actually process data. And what's very important for us is the performance of this data path across application APIs and the actual processing of the data. Also, we have this notion of event-driven processing for ad hoc processing. We now call it serverless because everyone now calls it serverless, and this is exactly the same thing. And I'll describe how we designed this system and why you have to take into account infrastructure and actual hardware if you're not developing on an Amazon cloud, and how you basically leverage the hardware in those scenarios. Just one thing which is pretty different in our architecture, and I'll focus on the data path just so you'll have some context. Traditionally, when you design a database, you build it through layers. You take block storage, and then you put like a file system on top of it, which adds a lot of chatter every time you open and close a file. You have different journaling to do and lookups. And then you place a database, which does a lot of overhead as well. Has redo logs and undo logs and index tables and distributed log management. So you can take the fastest storage on earth that is like millions of IOPS. You'll still have about 20,000 TPS or 50,000 TPS on your database or Cassandra. And that's because of all this serialization. So basically what we wanted to do is something which is more similar to like an in-memory database, like Redis, just implemented on top of Flash. And we had to use a lot of real-time technologies to make Flash look like memory. And I'll describe some things that we did over there. We didn't want to reinvent our API. So what we did is sort of a messaging bus where we can put a proxy layer that emulates any API we want. So this is how we can basically support traditional APIs or cloud provider APIs on top of our platform without sacrificing performance. And all those APIs are entirely stateless. So basically, you can write through one API and read through a different API without violating any state. So that's the general idea of the platform. There's also a lot of security but I won't dive into that too much. Just when I say real time, this platform generates about 2 million transactions per second on a given an individual server, which is about 100 times faster than most data platforms, and it serves them in about 100 microseconds across 99 percentile, which is, again, real time by definition. And when we look into this data path, so starting from a high level, how did we design the data path? So we have web servers which serve the transactions, and then the data path is basically managed by 2 layers which have different optimizations. So the first layer is the one that needs to respond to a database transaction, has to do it really, really fast. And the second layer, when you're talking to storage, you typically want to work in batch. Anyone that worked with storage know that, for example, you're trying to do maximum I/O depth at the storage layer. You want to do striping, so you have to aggregate more and more data and only then write it. So basically, we have 2 conflicting requirements on the data layer, one which have to serve stuff really, really fast, and one which basically have to do things really, really slow. This is why we broke it to 2 layers. And between them, in order not to have too much overhead, we basically have a shared memory. So basically, we have non-volatile memory, so every transaction in journal is committed into non-volatile memory, and then we pass it through a 0 copy, through pointers, to backend key value engine, which we develop and is extremely fast. It's also going to be open sourced. And this allows us to preserve basically 2 million transactions per second, this architecture, because we basically work at the speed of flash. We don't go through file systems or any of that stuff. We even have here a very cool concept where the processes, the Docker containers that work on top of the journals, if they fail, they can actually be restarted and go back to exactly the same state because the shared memory is presented as shared files. But if people want more deep information about what we do there, I can share later on. Here, basically, we have the Nginx. Nginx has a model which does all the sort of transaction processing, the API processing. And we emulate, as I mentioned, things like S3 and Kinesis and Dynamo. And they're basically models within Nginx. Now, in order to do it really fast, there are a bunch of requirements to do those things. So if you know how cloud providers work, they usually don't just use your flavor of NIC and you just work with it. Amazon basically bought a company called Annapurna, Israeli one, that basically has those network controllers. And so a lot of the networking happens there. If you read the Azure papers, they use FPGAs. I'm not sure what Google uses there, but also there's a lot of intelligence. So people are using hardware accelerator to do a bunch of things. So let's look at each one of those layers, how people leverage hardware accelerator. So first, you're doing overlay offload. So things like VXLAN or other more sophisticated overlays are basically being pushed to the adapter. And that's some of the things I've done in my previous job. Also, more and more encryption is going into the network adapters, like SSL and IPsec is going there. So you actually want to create sort of virtual interfaces for every tenant, because this first tier is basically serving different tenants. So for every tenant, you basically want to have a microservice that has one leg on sort of the overlay network and a second leg on sort of the internal fabric. Okay, so the first requirement is let's basically go to the NIC and say, please give me multiple virtual interfaces, and each one of those virtual interfaces may have other acceleration features. Another thing that you want to do, you don't want to have too much overhead on the transport between this front-end thing and the back-end data, so you want to use very high-speed RPC. One of the things that we developed also in my previous job, and it's open source and we keep on maintaining it, is an extremely high-performance RPC layer that knows how to leverage NIC semantics like RDMA or DPDK, if any of you is familiar with that. And this transport, for example, could do about 15 million messages per second. It's about different magnitudes than what you guys are familiar with. And it's about 3 microsecond latency for message between here and here. So it's basically faster than actual messaging within the same system. Okay, and that's running over a dual fabric of 100 gig. Now, one of the things that we had to do is serialize data. So basically, we don't just pass a buffer. We have to pass a message. So everyone is using protobuf, which is pretty nice. But the guy that developed protobuf, after leaving Google, said, there may be a better idea. And that's a protocol called Captain Proto, which was developed by the same guy. And one of the unique features of that serialization mechanism is that there is no deserialization. And that's pretty cool in some applications I'll show you. For example, let's assume that we ship a message all the way to our platform, and this guy has to replicate to another guy, but he needs to check what's happening in the packet, or like what type of data am I writing. And so you can actually do that without deserialization. And you can do all other pretty nice things without doing deserialization, and Captain Proto is extremely high performance serialization, deserialization protocol. Now on this side, when we process the data, if any of you did high performance before, then one of the things that you have to deal with is doing core affinity. You don't want to have your cores running around different CPUs, or basically doing threads, that having multiple threads that sort of run around different CPUs. What you want to do is basically have a single thread running on a single process and pinned to a single CPU. And this way you guarantee that the process keeps on working sort of real-time performance, maximize the CPU utilization, etc. So even people that will look at how do I optimize my Nginx performance, you'll see that people tell you to do like task set and things like that to make sure CPU cores in asynchronous architectures are sort of pinned down to the same infrastructure. So in our architecture, we basically break every node to virtual nodes, or those VNs, and every virtual node is on a single core. So this means that basically there's no locking, there's no context switches, there are no semaphores within a given VM. That really provides you this capability. Now there is some challenges here. For example, Kubernetes natively does not support CPU locking, maybe recent versions. With Docker, you can do that. With Docker, you can do CPU set, and you could basically set a container to a given CPU. Okay? So that's another challenge, and there are also other challenges. Doing shared memory between containers is not that trivial, and I'll talk about it. And you also want to have direct access to those flash. So I showed you that in order to maintain best performance, I basically have to deviate from the standard guidelines of how to do microservices and Kubernetes. So what are the challenges that we sort of faced? For example, we just showed you that I may have scenarios where I need multiple interfaces to individual pod, because I have a front-end overlay network and I have high-speed back-end network and maybe some control networks. And Kubernetes only supports single interface per pod. Okay, I need to access hardware primitives like SRV and NICs and NVMe devices and shared memory, and that's not that trivial. And we'll see some of the things that we did there. Also, one of the challenges, we make something work in Docker, and then we go to Kubernetes. No, it's done completely different. Security, priorities, things that work in one platform don't work the same in a different platform. So we had to do different things to overcome those, and mainly pull a lot of hair. If you were joking that the guy that does most of that work really looks like that. But so some of the things that we did in order to address and overcome those challenges, first we developed our own sort of networking and volume drivers. So we can basically, all the shared memory tricks, we can serve as eventually it's like /dev/something, so we can serve those through a volume driver while maintaining some security. And also the networking side, we can also automate and present multiple interface to a given container, as well as hardware-oriented interfaces. You also have to play a lot with privileges, because, for example, if someone is using shared memory or other things, requires different privileges than the traditional ones, and a lot of trial and error. And some of the other challenges, you change a Kubernetes version, and suddenly something that worked in the previous version doesn't work in the new version. So I hope it's going to be stabilized in the next versions. So just maybe a little 101 of how networking works in containers, and I had a nice blog post on more details on how to sort of bypass those and how to diagnose those. So you can go to that link. You can see that basically there are three approaches to networking in containers. Basically, every container has its own network namespace. So And Linux has a namespace where container can live only in one namespace. So there are two options. One is you have your host interfaces, and then you put all the containers in the host interface namespace, so the containers will see everything the host sees. Another approach is let's generate interfaces and then just give them away to containers. And how do we generate interfaces? There are three ways to generate those virtual interfaces. One is using a switch. And there are two switches in Linux. One is called OVS, Open vSwitch, which is a lot more comprehensive, have things like routing and ACLs and etc. And there is also the Linux bridge, which is a bit more primitive. Most overlay solutions usually use the bridge. And then you need some sort of a twisted pair because it's a switch. So a twisted pair, VTH pair, is basically a twisted pair. It's like a wire that has two interfaces. One plugs within the container, that one plugs within the hypervisor, and then the switch basically switches between all those different interfaces. Okay, so that's one way of generating those virtual interfaces. Another way is using a multiplexing approach where you create a driver that just shows itself with multiple interfaces, and you give those interfaces all the way to the container. And that's usually things like Mac VLAN, which does a multiplexing based on MAC addresses, or IP VLAN, which does the same using IP addresses. And this is typically slightly faster than this because this one is basically an extra hop. But there is another third option, which was used a lot in virtualization for high performance and in NFV, if some of you are from the telco environment. It's called SRIV. It's basically to tell the NIC, go create multiple virtual NICs in hardware and then expose those all the way up to the container. Some other nice things is those virtual NICs in hardware can also do things like QoS and security and other features for those virtual NICs. Okay, so basically we use that when we need high performance, and then when we don't need high performance, either one of those two. Okay, and there are more details. One of the things that allows us to expose multiple interfaces to the same pod is this project from Intel called Multus that allows basically to create multiple, to basically bypass this limitation of Kubernetes and present two interfaces. So this is a bit background on the networking side. And then we plug into applications. Think about things like Spark or any other application, TensorFlow, to do analytics. And we still want to maintain very high performance between those applications and the data. And everyone here is talking about block storage, and we've seen that in the presentation today. But usually if you really want to write cloud-native applications, you don't want the applications to have state. You want to have things that sort of commit on the fly. So if your microservice fails, you can restart it, just like object storage or NoSQL or things like that. And today there's only support for file system access through shared volumes in Kubernetes, but we actually wanted more expression like NoSQL or object or streaming semantics to go still high performance and not just by passing packets. Some of the challenge, if I have 20 workloads on the same machine, I don't want to have 20 TCP connections to the same database just on the other side, because that's going to be a lot of connections, that's going to require a lot of memory and going to just abuse my resources. It's also going to require a lot of startup time every time a process goes up, until it goes and launch and does all the logins and all the transaction against the data services. That takes a lot of time. So basically what we did, we took two services, one that exposes our system as a volume, and the other one that exposes our system as all the rest of the things. And usually the way to expose volumes is something called fuselib in Linux, if you're familiar with that. And one of the key challenges with it is that it's extremely slow. It's synchronous, it's blocking. We did some patches to it to make it work asynchronous. So it's about 10, 15 times faster than the traditional fuse driver. This can do a lot of IOs in parallel. And we've also contributed that back. But the really cool thing is not the fuse extensions, is what we call V3IO daemon, which is this thing that does all those NoSQL and object and streaming semantics. The way it works is basically the SDK that we have that expose all those APIs talks to the daemon through shared memory. So basically, there's no copy. The minute you put a message on the wire with this captain proto, a serialization protocol, it goes here. This guy doesn't have to deserialize. We mentioned captain proto doesn't require deserialization. Just looks at what needs to be routed and pushes it down to the wire. So then basically we could, within a few microseconds, send a message all the way from the application all the way to the backend data and back. So that can run about 100 times faster than what you're used to see. Those message queue protocols that we built using Captain Proto and shared memory can do about 1 million messages per thread. Okay, so this is pretty high performance. So, and those networking protocols can do about 2 million RPC calls per second on one node. So basically, this notion is very similar if you've written in Go. It's just like having Go channels where you just post a message, a request, an asynchronous request, give me something from the database, and then you get a return channel that gives you the response. And you could put as many requests as you want in parallel. So this is a pretty cool thing. It's lock-free. You don't have to block. You can just push as many requests as you want, and in parallel get the responses in different orders. And also we have a port for data frames in Spark. So you can actually write Spark data frames that will be persisted in our system, and you can query them back. Okay, and what it also allows is fast initialization of the containers because you don't have to open any connections. The only connection that you do is just open a shared memory file locally, and then you RPC or IPC to that. You don't have to allocate memory. Everything is zero copy end-to-end. We share the same TCP or RDMA connections here for all the different Docker containers. Okay, and we don't have to do any kernel modification or patches because all the code is user space. Okay. Any questions on that? Or so again, just an example, sort of taking the extreme. I know most of you guys probably will not take those extreme steps to performance, but because we're sort of a service provider, because this is a shared platform and a multi-tenant platform, we care about the aggregate performance and not necessarily just by our application. If I can push 2 million transactions on the same platform, it can serve 100 customers instead of one for the same cost. So this is part of the reason we're doing all that. The other reason is we're seeing this boom in IoT and real-time analytics that require some of those performance for certain workloads.
I have a question. This is applicable both for Docker and Rocket, or it is only linked with Docker?
So a lot of it is generic. Some of the issues are different, like exposing shared memory in Docker and Kubernetes is slightly different. The YAML files are different, the priorities are different, things like that. Yes, it's doable. We actually, we started with Docker. We haven't ported even everything to Kubernetes. We're still struggling with some of the containers. So in some cases, we still have Docker containers side by side with Kubernetes containers until we'll finalize the debugging process.
What sort of container density are you getting per node?
We don't need too much because those are typically heavyweight processes. Okay, so like on the data nodes, we have a process per core, usually, so it's about 20, 30.
So you max out the CPU, so they're typically CPU-bound processes?
Yep. Because we maximize that, we usually use servers with lots of PCI, lots of NVMe, so the bottleneck moves to the CPU. Okay, so that's on that front. Now, what we really wanted to give developers is the experience of serverless and event-driven functions, and we actually started doing it before we called it serverless. And if you're looking at serverless today, it has a bunch of challenges. If you look at the Amazon Lambda design, it's sort of a lot of things that Amazon does is sort of the first version is all about usability, not necessarily about efficiency. And that's what we've seen over there. There's also some public mentions of some of those things. First, the initialization time of a Lambda function based on that article is about half a second average. Worst case could be few seconds. Okay, this is pretty high, and also it's pretty much of a resource drain. One of the challenges with those Lambda functions is when you, for example, they charge you for memory times the amount of time you run the function. Every typical function that you launch the first thing it will do, it will go and fetch some data, some context. You got a web request with a user cookie. You go and you bring the user context into the system. And that may take you 10 milliseconds. So you're actually paying 10 milliseconds for every invocation of your function. And if you need to do 5 different calls in a synchronous fashion, you're basically paying 50 milliseconds. So if your overall task is 5 seconds, no problem. But if your overall task is like 50 milliseconds or less, if it's just a simple serving of a web page, which takes a few milliseconds at the most, then 80% of your time is spent on IO wait. And anyone here that codes in modern languages, whether it's Java with Akka or Go with Go routines, always thinks about concurrency. And here we have a system that by design is not concurrent. It just gets one thing at a time. So this article actually talks about why Lambda functions are not good for every workload, and it's around those things. The other challenge with Lambda is basically you have to create your data bindings because it's a stateless function. So where do you preserve the state? Where do you create this connection to your MySQL? So you put it somewhere in the header, and you don't really know when is it going to happen or when it doesn't. Where do you put the security credentials? Part of the function. You don't want it to be sort of hidden. So there needs to be other things like data bindings built into the cloud, into the serverless architecture. And that's something that Azure did, which is slightly better than Amazon. We also want to have everything that relates to connections. Let's assume I run 5 different instances on the same node. I don't necessarily want to create a database TCP connection every time I invoke my function. I want this connection to sort of be live and just pass transaction every time this is being invoked. And there are also other challenges, like they don't have any unified schema. I have to, for every type of event, I have a totally different schema, even for a thing that like event type could have been called event type in all the different types of events. But it's not there. So there's also some blog post I wrote about it. So we went and designed something which is trying to make a better implementation. We're also going to contribute that after we're getting into GA. And you basically have, there are 2 different data sources into Lambda function, into serverless. One is API, HTTP web calls. And basically you invoke a RESTful API, you want it to be passed into the function instance, usually synchronous. So I know IBM OpenWhisk is sort of doing it asynchronously, but you typically want to do it synchronous. You don't want to pass it through a Kafka and a gateway, etc., like OpenWhisk or some other technology. You just want to pass it all the way to the function and throw the response really quickly. Another source of events is everything that relates to data, like someone update an object bucket with a picture, you want to get notified, you want to create a thumbnail, some of the most common use cases, or maybe a streaming, like a Kinesis in Amazon. You want to throw a streaming into the system, and something listens on that stream or that message queue and just fetches messages and processes them. Okay, so this is more of the asynchronous path, and you have the synchronous path, and then you have some controller that needs to deal with the elasticity of that. So what this infrastructure requires, is also a set of metadata structures that are used. So in order to really maintain sort of a cloud native approach, all the logs are not stored in the function. They're basically stored in a shared message queue. All the state of tracking the state of those functions have to be stored in sort of tables. There are other nice things that we can do, and I think also Redis and other databases can do, is do atomic transactions on the data. So in order to do rate limiting calculation, we can just have one reducing the number of credits and one adding credits and doing test and set. So this way you can lock when there's no credit. You don't have to basically have a separate process that tracks it. You could just use the database as your synchronization point. So this is basically how we designed this. And also about the efficiencies, first, you want to have minimal amount of hops from the API gateway to the function and back. You want to have more parallelism. So think about having micro batches and having multiple Go routines for every function in order to add more concurrency. And also those updates to the data could be on micro batch level. So for every 5 invocation, I can update the record on the database. I don't have to do it for every invocation. So this way I reduce the overhead on my database. Again, and some of you guys may design things that are very similar to this and not call it serverless. So how would you code to that? So this is a very simple example of an HTTP request, basically throwing an event with the context. Basically, the log stream is built into the context. You don't have to write code that goes and initialize the log stream and all that. That's just an object that you push data into. Another nice thing about this data binding that I mentioned, you want to bind the data directly in the context. You don't want to deal with the initialization of the database or the object storage that you're dealing with every time you run the function. So basically, you can specify that in the context and just use that in this case. And we also abstract those data as a sort of generic class that could work with different types of data sources. The other thing that's a little more sophisticated is on the data integration. And we spoke about this asynchronous problem with Lambda and parallelism. So one of the things that we did in our platform is this notion that everything could be a stream. It doesn't matter if it's files or tables. Actually, file in our platform is a record in a database where one column is the file. So basically, we treat any data as a database, and we also treat any data as a stream. So basically, we can run continuous query, say this is what we're looking for, all the results, whether those are ad hoc changes or whether those are just queries on a batch, will stream into workers. Okay, and workers you may have 4 workers. So basically, we have to shard the result set into 4 different workers. And there are a bunch of databases that support that notion. And every worker that works on the data may return some updates. So for example, I have a table, I have an object, I want to tag that object or add some metadata. I can return that back as a transaction. One of the key challenges in those areas is what's called exactly one semantics. What happens when a function fails? How do I know if the function actually executed or not? So those are usually being done through atomic commits into the data itself. Okay, so that's in generally one of the key challenges in Kubernetes that we see is that let's assume that we have 4 workers that need to work on a stream. You have a Kafka stream and you have 4 workers and you've sharded your Kafka to 4 different shards. How do you create a deployment set in Kubernetes where each one knows which shard it's going to take? And it's not just about Kafka. Let's assume you have a bunch of pictures that need to be processed and you have an elastic service with a bunch of pods. How does each pod know which shard or which objects to go to? One of the hacks that we did here, we basically use stateful set in Kubernetes because I don't know if you know how it works. Basically, it gives each one of the pods a different name with an index. So you can just extract the index from the name, and then you know for each one of the pod what's the index. We hope that in a certain point, Kubernetes will add index to pods or some other way to tag a pod and give it some sort of a value different than the other pods. So that's another thing that we did on that front. So I'll give you another example of how to use this framework. And this is a simple way of taking a file that was generated, scanning it for example, social security numbers and credit card numbers to just identify if this file has a sort of sensitive data. You could see that using those primitives I mentioned makes it extremely simple. So basically, we can cast it to the relevant type that we need. We can push the data. So instead of having the function go and read the data and wasting time, basically the function can already get the data into the object context. And then we can take the same data and tag it with attributes. So basically, we take the same data, treat the same data on one end as sort of a file, and on the same time, the metadata on that object could be treated as a record in a database. So this is what we do on that. Another very useful semantic is to have counters which are distributed across functions, because sometimes those functions analyze some content, and you want to know, like in this case, how many files actually have social securities in them. So we can add the distributed counter to the context of the function and it makes the life of the developer extremely easy. Now, all of those commits don't actually happen during the function execution, which is pretty cool. So only when you finish the function, there's like an atomic commit process. So if this atomic commit fails, your data is intact. Okay? Another example, which is maybe slightly more cool, is extracting data from pictures. And this is using now the same data. The challenge is that some libraries only have file access, like those EXIF libraries for JPEG. They only work when they actually see a file. So if you'll work with like Amazon, you have to read the data from object, convert it to a temporary file, and then run some processing on top of it, and only then generate the metadata and store it somewhere. So by being able to see the same object on one way as a sort of mounted file on the same time as an object or as a table, you can actually do those things in place, like I'm doing it here. Okay? And we mentioned also we can take the thumbnail and just throw it in as yet another blob record for the same object. So this is this, and this is just an example of one application that uses all those things that I talked about. So you can ingest the data as a picture into the platform. You can run this extraction functionality that I mentioned that just looks at the EXIF data and generates tags on the data based on like geolocation. You can run things like TensorFlow to actually go and do deep learning on the same pictures while this is running. They can actually run concurrently. What we demonstrated is actually two TensorFlow processes, one doing facial recognition, one doing sort of scenery recognition and geolocation extraction all at the same time. Having something like Spark looking at the same data and running analytic queries on that and serving all that data through a dashboard, all that in parallel. And this is enabled by having this sort of continuous loop and having everything looking at the data in different ways, but the same data.
So all this is in Kubernetes? Or it's a platform?
So our platform uses Kubernetes in order to deliver this. And some things are still not Kubernetes because of those challenges that we haven't figured out. Some of the things are still in Docker containers. So basically, if you're asking about how it's deployed, basically we have our platform that has a lot of Dockers inside, and then you have Kubernetes that can serve the different workloads on top. And the workloads could be either a stateless event-driven processes or just traditional workloads that can look at the system, whether through a file or object or other APIs. Okay? So this is it. I also have a backup slide if anyone interested how we're designing for abstracting the different data layers. And that's pretty generic. So one of the things that we want to do when this will be contributed to the open source is try and map those to traditional data stores so people can use the same abstractions, same APIs with like Kafka or Cassandra or any of the other data sources. Okay, any questions?
Kubernetes Fission, cannot be used somehow?
Sorry?
Fission?
Not
Is that the service functionality?
those things are nice, but they're more designed for HTTP, web developer, Node.js. They're not even close to the performance and optimization that those things are designed at. So we wanted to really optimize the data pipeline all the way and make sure we maximize the CPU utilization, reduce latency. Those other things are basically using a lot of blocking, and they're not really optimized for data streaming. So mostly HTTP requests and things like that. Any more questions? Yep.